I was invited to do this to try to explain how all this stuff works, rather than specifically what it might be used for, and why it might be regulated and all those interesting stuff. So most of this is going to be about trying to hand wave a lot how it works, and a little bit on why now, why has it happened now? And the graph on the screen at the moment is kind of why now. It's because it's got progressively cheaper over the last 50 odd years to buy memory and buy storage space and CPU power, and we'll come back to that later on. So there we go. I'll say up front, so I'll circulate the slides. This slide has some hot links to the bits that I use to try to find my own way around this space. So these are the resources I found, mostly YouTube videos. They're all very friendly. So if you fancy spending 3.5 hours watching this lot back to back, then you'll have seen most of the stuff that I looked at and found very useful introduction to how all this works. So that'll be there for those who want to have a look. Oops, I didn't mean to do that. Right. So the AI journey, first of all, is a quick catch up. It's about 80 years since neural network mathematics was first proposed, 1943. 1951, the first artificial neural network was created with only 40 neurons, and what a neuron is, we'll talk about later. The term AI itself, artificial intelligence, dates from 1956. Machine learning from 1959. ELIZA, the first chatbot, although a very simplistic one, is 1964, 65-ish, so that's as old as I am. Something called backpropagation was invented, and that will be explained a little bit later on, and that's kind of key to how the neural networks work and how they train themselves. 1975, the Cray 1 supercomputer, which when I was young was considered the nuts in supercomputers, ran at 260 million floating point operations per second. So if you gave it two numbers with lots of digits after decimal point and told it to add them or divide them or multiply them, it could do about 260 million of those every second. That was considered jolly fast and sort of thing you could do weather forecasting with. The AI winter, 1984, was a period of time when AI was considered a complete waste of time, and there was no money from research councils for it. But some people soldiered on. First self-driving car, 86. Something called convolutional neural networks were invented as an idea in 1989. Then people got a bit worried about what might happen if artificial generalized intelligence, AGI, appeared, and whether or not it would look upon us benevolently or decide to annihilate men and women. Deep Blue beat Garry Kasparov at chess in 1997, but how it did it was completely impenetrable. The software underneath it all was kind of more AI, and as we'll see, if you look under the bonnet, it's unintelligible how it comes to its conclusions. The Cray supercomputer from 1975 was trumped in 2013 by a computer running at petaflops, which is 1,000 times, I think, megaflops. No, it's 12. It's 1,000,000 times faster than a megaflop. So computers are getting a lot more powerful, and that was to some extent driving the ability to build larger and larger neural networks. Until by 2022, we end up with ChatGPT, which is what sort of kicked all this off. So the current world's fastest computer, the Hewlett-Packard Enterprise Frontier, runs at just over 1 exaflop, which is 1 followed by that many numbers floating point operations per second, and it does 62 gigaflops per watt. These things are unbelievably energy intensive as well as compute resource intensive. And the HP Frontier is 30 times faster than that thing from 10 years ago, which in turn was 130 million times faster than the Cray 1 supercomputer that those of a certain age will have heard of and have worshipped in its day. So it's that kind of advance of technology which has finally reached a sort of tipping point that made all this possible. But most of the foundations of how it all works are kind of 60, 70, 80 years old. When I sort of first came into computing in short trousers back in the 70s, computers looked like that. Storage looked like the things on the left. And at the time, there were kind of 4 AI sort of technologies around which I dimly understood. One was symbolic knowledge-based logic. Another one was Bayesian networks or fuzzy logic. And then there were things called expert systems, and it wasn't terribly clear whether that was a third class or just as a general term for the first 2. And there were things called medical logic modules around I'd heard of and occasionally encountered. So, for example, rule bases and expert systems. So if I give a computer a rule base, like if X croaks and eats flies, then it's a frog. If it chirps and sings, it's a canary. If it's a frog, it's green. If it's a canary, then it's blue. If that's my knowledge base, I can ask questions like Fritz croaks and eats flies, what color is Fritz? And the logic engine will combine the if-then clauses at the top and come up with a conclusion. And it's very deterministic. There's no kind of uncertainty anywhere in there, and you have to put in exactly the right inputs before you can start looking at the values in the if-then clauses. So you could do toy experiments, but anything big very rapidly started to spiral out of control, and your ability to alter the knowledge base or meaningfully put new input into it that would prompt it into giving a useful response. But people persevered, so there were a thing called medical logic modules in something called Arden syntax, which was I think an HL7 standard, possibly still is, and was all the rage in the late 1990s for writing down platform independent encodings of interesting rules. This one is a classical example of what to do if someone's got blood pressure problems. And there were others, but they were, as soon as you got to some more complicated medical care pathways, they started to get more difficult, often because those pathways themselves are not entirely deterministic or art than science. But people sort of soldiered on with things called decision trees. So, coming at the top, if patient's underweight, yes or no. If they are underweight, do they have a fear of weight gain? If yes, then the diagnosis is anorexia nervosa. If no, have they got some other emotional disorder? So this sort of decision tree, a very kind of binary decision point at each branching bit of the logic, they were sort of quite popular and got quite large and unwieldy and impossible to maintain for more complicated sort of diagnostic processes or other medical processes. And the kind of a big Achilles heel was that in most cases, the set of things that you could measure across the top were not exclusively linked to one diagnosis. Just because somebody purges doesn't necessarily mean they've got binge eating. They could have some of the others. Some of the options are more likely. And so they began to realize there was this more kind of weighted input that you depending on which combination of the settings across the top that you said the patient had, that made some of the bottom things more or less likely. And it wasn't really a case that there was only one right answer. There was sometimes one that was more right than others. And the difficulty in this kind of style of logic was working out the weightings of the blue arrows. So how much does each one of the inputs across the top contribute to the things at the bottom? But people experimented with these kind of neural network processes and then sort of started stacking them together and say, well, okay, actually, perhaps I should have a series of more basic inputs at the top. And in the middle, I've got these sort of intermediate diagnoses or intermediate states, which I need to work out whether they're true or not. And each of those is influenced by the things higher up. So they began to sort of stack these weighted lines and nodes one on top of the other. And that kind of broadly is the underpinning of the idea of a neural network or fuzzy logic. And they started to get more and more complicated as processors became more powerful and storage became cheaper. You could build larger and larger ones of these things with more and more layers between the inputs, typically on the left, and the output on the right-hand side. But that process of working out what was the exact correct value of the weighting, to what extent does any node make the next one in the chain from left to right more or less likely? There were no resources for those. And if you kind of made the best guess and then the answer on the right-hand side came out wrong, then how would you work out which of your weightings was in fact the one that had caused the error? And then people started thinking, well, maybe if we had enough data on the left-hand side, the bit in the middle could kind of train itself. We wouldn't have to calculate those numbers in the middle at all. It would kind of work it out for itself by some magical process. At the time, sometimes called self-directed feature engineering. So the features are the things in the middle. Not only do we not know what the values of the weightings are, we don't need to even know what the nodes, the colored circles, even stand in for. So in the previous examples so far, we've kind of had in the middle of the network, the idea of, is the patient overweight, for example. In this world, we don't even have to specify what each of those nodes corresponds to in the real world, nor how it influences the next levels down. All we care about is the inputs, the left-hand column, and the right-hand column, the two yellow outputs, and everything in the middle is entirely magic and not under our control. The only drawback with this approach is that because we've no idea what's going on in the middle, the notion of explaining how the engine ended up with this result is essentially impossible. Not very difficult, impossible. So the idea of explainability, if you go down this approach, essentially goes in the bin. But press on. So I'll sort of try to walk you through, and apologies to those who already know all this stuff, kind of how this works with what appears to be the kind of standard trainee example of how to build a neural network. So we'll focus the easy bit first of all on the left-hand side. So this is derived from the MNIST dataset, and I can't remember what the MNIST dataset stands for, but it is a publicly accessible library of 70,000 or thereabouts handwritten digits, the numerals 0 through 9 in multiple different handwritings. And each of those digits is represented on a 28 by 28 pixel grid, where each pixel in the grid can be given a value from full black to white, which is represented as a number or a fraction between 0 and 1. As to how white or black it is. And all of these 70,000 handwritten photographs or digits or whatever have also been annotated to say what the number actually is. And so if you take those 28 by 28 pixels, which you can see drawn as a box, but you just sort of joined up the second row to the end of the first row and flattened the whole thing out, you'd have 784 dots in a row. So that's your input layer. So on the graph on the right-hand side, the neural network, the input layer on the far left actually has 784 input nodes, which you set with a number according to the value from the grid, the square or the photograph of the letter on the left-hand side. And then between the input layer and the output layer on the far right-hand side, which says, you know, basically we want to know, is this a 0, 1, 2, 3, and so forth up to 9? That's the answer. And in the middle are the hidden layers, which I think are genuinely only the two in this kind of standard training example. So all the input nodes have an initial starting value, which is known as their activation. And that, as I say, is the number that corresponds to how white or black or gray or whatever the cell is. And it will, as I've said before, you might have expected it to be a number between, say, 0 and 255. Some other way of, or more common way of representing grayscale in computer terms. But in most cases, one of the key characteristics of the input layer is you want to represent whatever it is you're representing as a number between 0 and 1. Otherwise, the mathematics that follows starts to get rather horrible. So it might originally, in the original source, have been represented as numbers between 0 and 255. But in order to fit it into a neural network, you collapse that bound to a number between 0 and 1. And then each of the activation input nodes has a line to every single one of the nodes in the next layer down, and all those lines have a weighting, and the weighting can be either positive or negative or 0. And for each of the nodes in the next layer down, so the second from left layer of nodes or neurons, you calculate a number by multiplying the activation values of all the nodes linked to it by the weight of the line joining the two, and you sum all of those up, and you add a bias, and then you do a fudge factor to turn, what it's likely to be quite a big number to start with, certainly bigger than 1. You then collapse it back down to another number between 0 and 1 by passing it through a magical mapping function, so that the next layer, the first hidden layer, then behaves like the input layer. You've now got a number of activation values, which you've calculated by multiplying all the nodes and the input layer and the graph and the arcs, sorry. And then you can repeat that exercise from the first hidden layer to the second hidden layer, and then from the second hidden layer to the output layer. You just do the maths. And what you get in runtime, and there's the link at the top, if you go to that, you can actually play with a web-based implementation of this, and you can draw your own numbers and see how well it works. So you can see here we've got on mouse disappear. There we go. We've got some numbers that are just full black. Here's a fairly dark grey one building up to a white bit, and so on. And then they would be multiplied by the nodes to generate some new activations of the first hidden layer, do the same process to generate the second hidden layer, and then finally you generate the output layer. And in most cases, what you want is the output layer to match the input. It was, in fact, a 4. So the brightest option, one with the highest activation value calculated in that way in the output layer, is the most likely answer. But as you've seen, there are an awful lot of moving parts. There's 12,960 weighted lines to adjust. And so how might, or in fact, how did the machine learn all of the weighted values for itself? And the way that you do this for all of these kind of technologies is first of all, you divide your data into a training set and a test set. So that's your 70,000, handwritten numbers where you know the answer. You divide them into a training set and of maybe 60,000 and keep 10,000 back in reserve as your test. And you then set all the starting weights of your neural network completely randomly. You then feed in one by one all of your training examples and do the mathematics that we've described to generate an output number or numbers. And when you finish doing that, you compare what the neural network said the numbers are with what the real answer is. And then you generate a cost function, a mathematical equation of huge complexity that allows you to score how wrong the network was. And you then use this back propagation mathematics to decide which of your weightings, if adjusted, would do the most to make things less wrong. So you can't calculate the first time round the loop or any time round the loop exactly how much to adjust anything. All you do is work out, let's say, the direction of travel you need to go in for each of the weightings. And essentially the mathematics behind this is A-level further maths, but operated at scale using predominantly the chain rule and differentiation by parts for those who did that bit of mathematics. So you do this bit of maths and that allows you to, as I say, work out the direction of travel that each weight needs to go to reduce the incorrectness of your network. And then you nudge them all a little bit in the direction suggested. And then you redo the whole exercise. You reclassify all of your images, put them back through, and then recalculate the difference or the direction of travel you need to go to make things less wrong, until eventually the whole thing stabilizes and you find that tweaking, making more changes to the weighting factors doesn't actually make any difference to the overall accuracy of the algorithm. And that can take a while. and certainly will take quite a lot of computing power. And so in the early days, particularly, the process of training, iterative training, would stop when you run out of compute time or coffee or got bored. And again, as compute power has grown, our ability to do this for longer and train on bigger data sets has increased very rapidly in the last 20 or so years. However, once your network is performing at a level that you don't seem to be able to improve any further, you run the network again on your test set just to confirm that it is equally accurate on a set it's never seen as it is on the set you've been training it on. And that's one of the checks to make sure you haven't overtrained and you're exploiting unexpected properties of the training set that are not necessarily typical of the values you're going to use afterwards. And if you really want to go the whole hog, you might rerun the whole process multiple times to see if you always get the same final score. In this case, the final score might be that 97% of the time it guesses right, which I think is about what you get for this particular neural network. So again, to try to explain a bit what's going on in terms of this sort of cost function. If you could, in theory, produce an enormously long equation with tens or even hundreds of thousands of terms involving all those inactivation values and weighting factors and so forth. And if you plotted that on some huge multi-dimensional space, you would get a very wobbly imaginary surface that Doctor Who might be able to understand, but we can't. But the mathematics of it is fundamentally the same as the more familiar x and y, just 2 dimensions. There is a curve in this case. We know that there is a minimum value where the performance is as good as it's going to get. It might not be perfect. And so that's that bottom of the curve. We have randomly positioned ourselves where the blue blob is. We want to be at the bottom of the curve, but we don't know where the bottom of the curve is because the complexity of the real equation in an AI setting is just too difficult to calculate where the bottom of the curve actually is. In simple maths like this graph, you could work out straight away what the right answer is. Correct value of x and y are that identify the very bottom of the curve. But when things get complicated, the best that you can do is to work out the general direction that the bottom appears to be. So it's like descending a hill in fog. You know which way down is, but you don't actually know where but you can't see the bottom. And so you trust your luck that if you just head down, you'll eventually get off the hill. And so you kind of make that small adjustment, and then you test again and see is down still in the same direction. So one of the problems with the real world of AI is that the curve, if you like, that you get in a multi-dimensional space is not as simple as the one on the previous chart. It's more like perhaps this. And so there are a number of risks involved in how you choose to adjust your weighting factors. You know the direction you need to adjust them each in, up or down, or leave them alone, but you don't know by how much. So one of your problems is getting stuck in a local minima. So if you don't adjust it by enough, you'll find that you settle into a spot that is has a hump in the way. You're not going to get over if you just keep nudging it very small amounts. On the other hand, if you nudge it by too big an amount, you could end up wobbling from one side and backwards and even flying out the top. So there's a kind of black art in deciding exactly how much to adjust your weighting factors by in the direction that the mathematics tells you that you should. The disadvantage of doing it in small steps is A, it will take a very long time to eventually reach a stable point, and B, you're more likely to get stuck in a local minima on the left-hand side. The disadvantage of doing it in big steps, or the advantage is you might get to the bottom, the true bottom quicker, but the disadvantage is you might fly around all over the place and get a chaotic thing. So the process of training involves monitoring the curves of what is the trend? How quickly is my accuracy improving? And does that tell me that I'm making the steps too small or too big? And that's very much a judgment call of a skilled AI engineer. And I say for the neural network that seems to be the standard go-to toy example, which is this recognition of handwriting numbers, a trained model is about 98% accurate. No one seems to be able to get it much better than that with the data set as provided. But one of the obvious questions is, well, okay, we didn't declare what the features that should be looked for were, the hidden layers. So the feature engineering as well as the weighting has been entirely induced by the machine from the data. So what's it looking for? And we might imagine, because this is how we would do it, that those dots in the middle, the two middle hidden layers, corresponds to kind of real things in the real world. Maybe one of them says, is there a circle and nothing else? Or another one looks for vertical lines and so on, the sort of substructures of the digits, how we might do it. But the answer is no, it doesn't do any of those. If you actually look at what the second layer neurons are looking for, they're looking for nothing recognizable at all. And one of the other consequences of the way it works is if you feed it completely random input, white noise, because it's been trained to produce one answer, it'll say a random number is a random background of white noise is confidently it's a 5 or something. So one of the consequences, the way these things work, is that if you give them the wrong kind of input unwittingly, then you can generate very incorrect output. So back to the kind of the history of AI stuff. One of the other kind of black arts that developed was deciding how many hidden layers you would have, and that was to some extent forced upon you by the compute platform limitations. But in addition, you might decide that you want to deliberately throttle things. So this second row, far right, deep convolutional inverse graphics network, one of the decisions in the design of that one was to say, well, let's try to force it to constrain down to a small number of features in the middle of its kind of thinking, if thinking is the right word, and then expand back out from there to the input, the output layer. There are obviously others in this neural network zoo, as it's called, with different overall architectures of how they decide to join everything together. But over time, the number of neurons we've been able to put into these neural networks has grown. So the graph at bottom left sort of shows the rate of growth of the number of neurons in sort of typical AI neural networks, which have doubled roughly every 2.5 to 3 years. So it's a logarithmic scale that we're seeing here. And on the right-hand side is the number of neurons in the brains of sponges and roundworms at the bottom up to humans. So by 2015, we were kind of approaching the level of a frog, and that's about a decade ago. But we're kind of approaching human levels of number of neurons now. So at this point, a detour into the sort of soft underbelly of even the technical part of neural networks. I've said that there are certain aspects of neural network engineering and curation, which appear, as far as I can tell, to be black arts and experience, working out how big a step to take in the direction. That seems to be, something you learn by experience rather than by theory. And also deciding on the precise architecture of your neural network is another one. But even the mathematics of this has some sort of issues. So I said earlier on that when you multiply the activation values of one layer of the network by the weighting factors to generate the activations for the next layer in, that you would end up with numbers bigger than 1. And the mathematics of those can get quite horrible as you multiply them. Big numbers multiplied by big numbers get to very big numbers. So in order to try to sort of constrain the thing, they pass the raw mathematical product of all those multiplications through what I would call a squishification function, and there are a number of them. So the sigmoid function at the far left basically says, if the number is close to 0, I'm going to leave it more or less as it is. But as the actual number I got given gets bigger and bigger and bigger, I'm going to squish it more and more, and so on. And if it gets below 0, then I'll do the same thing but in reverse. The kind of more commonly accepted algorithm now is this rectified linear unit, I think, ReLU curve, which was an attempt to simulate the fact that neurons they're either completely off or on to varying degrees, but there's no kind of meaningful negative value of the neuron. And so the ReLU function says all values that I get by multiplying activation layers, levels, activation values, and weightings, all values less than 0 are 0 once I pass them through the function, and everything after that is just left more or less alone. There's another variant that some people use called softmax, and there are a range of others, but these kind of squishification functions to control the mathematics whilst at the same time sort of vaguely being inspired by their understanding of biology are again a bit of a black art as to comparing which one to use under the various circumstances. They're designed to boost the signal to noise ratio, but they are responsible for producing their own distortions, which is why they have their own fans and issues. The stochastic gradient descent of the cross function, so the walking downhill through the fog by nudging all the weighting values a little bit here and there, incentivizes a certain amount of overconfidence in the training. So, for example, that result where if you feed white noise into the handwriting recognition thing, it'll confidently give you a digit because it's being trained to produce one answer. And so given that it can't tell the fact that you've given it fake data, it'll just carry on doing something. And so that's one of the many causes of hallucinations that most of us will have heard of in the context of ChatGPT. The issue of this sort of feature engineering and embeddings, how do you, in the case of those handwriting photographs, it was reasonably understandable how they turned what we would recognize as a JPEG or GIF image into a flattened out set of 784 input layer nodes. But if the input layer is actually derived from text, so perhaps from what your prompt into ChatGPT, how does that get turned into fundamentally a series of numbers between 0 and 1? Or if it's a set of SNAMED codes, if ultimately they've got to be 0 or 1s, what is that? So there's quite a lot of mathematical tricks and simplifications that are used in that process of sort of shoehorning the real input data that you've got into this very specific mathematical input format. And as I said, the overall architecture of the neural network itself, something called hyperparameter tuning, that's the bit largely about how big a step do you take in any direction. They're all suck it and see black arts. A lot of it seems to be about set it up how your gut tells you is probably the right way to do it. See what happens. If the model doesn't seem to train in the sort of time you've got available, then maybe you need to go and tweak some of the things that you've done, either to take bigger steps or change the network design, but use your experience. And lastly, you will have heard of overfitting, that if it's possible to end up with models that are too complicated. If you give it too many neurons, it will see complexity where there isn't necessarily complexity. Equally, if you train it with poor quality data, then garbage in, garbage out still applies. So a little bit on why now. Compute platforms in the here and now. So this presentation is brought to you by Lenovo ThinkPad P16 Generation 1 laptop, NHS developer machine. It's a fairly fancy Intel i7, 64 gigabytes of memory, and critically, it can do 85 gigaflops. So 10 to the 9 times 85 floating point operations per second, and it needs 157 watts to do that. So for every gigaflop of every 10,000 million multiplications it does, it takes about half a watt to do that. The fastest computer on Earth, by contrast, is a scary beast capable of 1.1 exaflops. That's a 10 followed by 18 digits. Consumes 21 megawatts as a small power station when up and running. It's actually based on, it's really what you get if you join 9,000 computers together, or 9,500 computers together. And each of those computers is based on a not particularly exciting AMD branded CPU. It's not that much better than the one in my laptop, just there's 9,000 of them. But they're not the real meat of the beast, to be honest. Their job, the EPIC AMD processor in the middle, is purely to coordinate 3 mind-bogglingly expensive graphic processor units, GPUs, that each of them has. And each of those graphic GPU is about £20,000 retail market. So there's 60,000 quid's worth of, 60,000 quid's worth of GPU per node, and there's 9,000 nodes. So it's huge computing, a lot of wiring to join it all together. Not quite sure what it does. But yeah, so there you go. My processor in the middle of my laptop it costs £360 and is benchmarked at 32,000 somethings. The one in the Hewlett-Packard computers is about 60% faster and costs about £878 per chip. But I would need 13 million laptops to produce the same horsepower as that Hewlett-Packard computer, and that's the sort of beast which is now being used to train your neural networks for ChatGPT. And it will be dreaming for some weeks before it finishes training itself. But again, why now? It's to do with reaching the sweet spot of the ability to store vast quantities of input data, the whole internet almost, and the reducing cost of the processing power required, particularly the graphical processor units, to multiply all the numbers together to calculate all of those many activation value times weighting values. So the vast majority of the mathematics is just to multiply 2 floating point numbers between 0 and 1, the activation value and the weighting, but just do that for millions upon millions of neurons repeatedly. You'll have heard of transformers. So the T in GPT is transformer. So what's a transformer? I kind of alluded to the fact that the input in generative technologies like Siri and also ChatGPT is sequences of things, of words or possibly digital images or sound. And the output is also sequences. It's text, GPT's case. In others where you've got text input and video output, it's different kind of serial data. But the output is to be generated one word or phrase or pixel at a time. And so the output is sort of described as being a transformation of the input. In other words, predict what will be next in the sequence, the output sequence, given the input sequence. And what sort of the last piece of the ChatGPT puzzle dates back to about 2017, and a publication by Google Research Labs. And the key innovation in it all is something called multi-headed self-attention. What this means is that the model, the neural network, learns which tokens from either the input that you specified, and which obviously doesn't change, or the text generated from it so far are most relevant to what the next word probably should be. And critically, the window for where the relevant tokens can be found is the entire document being generated and all of your text, and not just the most recently generated bit of it. The older technologies, limited largely by their compute platforms, had a rather shorter and sliding reference window. They essentially would look at the last 10, 20, 30 words that had been generated so far and use those to decide what the next word should be. And it's that way of working. It's the reason why when you use ChatGPT, you may have, not particularly made note of the fact that its answer appears to be typed sort of one word at a time, or appear in sometimes 3 or 4 very quickly together, and there's a short pause, but you can see it sort of, if you like, thinking. And you might have thought that was just sort of prettification or some clever output just to make it look more natural. But actually, that's you watching it doing that process of seeing, what have I said so far? If I feed that through the neural network, what's the next word supposed to be? Oh, it's probably this. So I'll put that on, and then I'll go around the loop again. And that's how it works. So again, why now? Massively larger compute platform. ChatGPT 4, the input can be 52 pages of text. So if you think of those 784 dots in our handwriting recognition, digit recognition thing earlier on, 52 pages of text, if each input node is a word or maybe a letter, there's a lot more nodes in the input layer. The output can be in any one of 26 languages. There's 100 hidden layers between the input and the output, and altogether 100 billion neurons, circles in the network, and 100 trillion synapses, or the lines in the neural network. And that kind of compares with about 86 billion neurons in the human brain, and between 200 and 400 billion stars in the Milky Way. So we're approaching that kind of size of engineering. One of the concerns with the approach has been, well, if you've got such a huge network, rather than learning or abstracting anything from the data that you feed it, does it just memorize it all? And so all it's doing is just churning out pre-recorded information. So that's one of the sort of challenges to this approach. And the graph at bottom right is aiming to say, no, that doesn't seem to be what's happening. We've tried feeding it randomly labeled data and properly labeled data. So the randomly labeled data is trying to deliberately lead it astray and see whether it sort of, does it make any difference as to how quickly it trains to generate stuff. And the bottom graph shows that something is definitely happening with properly labeled data. So it is indeed learning something rather than just memorizing the entire training set somehow. Next bit, generative AI versus generic deep learning. So all the hoo-ha has been about generative Siri type stuff of, what's the next word? And it's important to remember that deep learning is a different sort of, or machine learning is different from this. But to recap, this notion of attention, multi-headed attention, that this Google Research Labs paper from now several years ago, which was entitled, I think, "Attention is All You Need." It's the most relevant approach when both the input and the output are going to be serialized data like text, images, or sound. But they can still be relevant when trained on sort of longitudinal individual patient data. So there may be some overlap between the generative approach and the sorts of things which we ordinarily would have used more mainstream machine learning approaches. So if I were to feed a suitably trained variant of GPT the whole of Mrs. Miggins's medical record and say, what should we do next? What it'll actually come up with is what do people usually do next? And ChatGPT, in fact, already does that. You can type in a medical record and say, what's likely to happen next. Current applications of AI, I'll probably skip over, but obviously chatbots like Siri and Alexa, self-driving cars, mobile phone photo filters, they're all based on AI to varying degrees. Interpretation of X-rays, there's AI weed recognition, so there are now trucks driving around in farms with a real-time ability to photograph the floor in front of them, work out what's weed and what isn't weed, and zap the weed with a laser rather than pouring weed killer all over everything, and so on and so forth. It's all over the place and everywhere. So what does all this mean for us? So one of the questions is, so coding's redundant. Computers can read now. We don't need coders. Versus the alternative hypothesis, coding is here to stay, but AI can add value. And there's a series of papers on the right side of the screen from last couple of years exploring the issue and saying, well, hang on a minute, it's coding and traditional coding activities are not going anywhere soon. There are some significant barriers to be overcome or hills to be climbed. But in theory, the consensus appears to be that a suitably trained AI could auto-code the electronic record of the clinical notes with reasonable accuracy to targets of either SNAMED, ICD, or OPCS, or even directly to HRG4+. So if your final goal is to get to a costing system, it may be the case you don't actually need to go via ICD or OPCS at all. Just train it with a vast set of medical records and say this was the HRG4 code that this record got. You figure out why in those hidden layers. I don't need to know, as long as you come out with the right answer. That's good enough for us. And the major drawback in exploring just how successful that might be is the lack of availability of the data to train the machines on, rather than anything else at the moment. So the next part, or the final part of this, and the reason why I suggested I might need longer than 45 minutes, which you've already had, was to sort of give you some a taste of where some of the issues are in ChatGPT, particularly by way of, for those who haven't had time to sort of poke it with a more cynical stick to see what's going on. So I've been kind of experimenting it, as probably we all have, off and on over the last few months or so. And I'm going to go through 4 or 5 questions that I asked just to see how it performed and look at where it fell short, and possibly a way of explaining how that might have happened in terms of what I've covered so far about how it sort of works. So one of the questions I asked it was, I was trying to work out how to dress this up. The basic question was this graph on the bottom right-hand side, which is how often do GPs using EMIS in dark green enter any of the codes from SNAMED in the descent of viral disease. So there's quite a lot of those codes, and obviously upper respiratory tract viral disease is going to be one of the more common ones, but there are many others that they could choose from. So how often do any of those codes get put in by EMIS clinicians versus TPP doctors if we standardize the actual numbers to a constant population? And as we can see, they're not the same shape. Well, they're sort of the same shape. The pandemic clearly did something. So these are annual figures, but there appears to be a sort of systematic different extent of use of that section of SNAMED over time in those two systems. So why might that be? So I was trying to dress this question up to see what ChatGPT made of it. And this was by way of trying to see, if I present a sort of what looks like an analytics question, what does it do? So I recast that particular problem in the following way to ChatGPT. So my prompt was, orders from our catalog are placed via our single website, and orders then assigned randomly for fulfillment by one of 2 warehouses. Each warehouse uses a different IT system to record their shipments. So that's code for, we send basically the same patients to the same doctors, but they're using different IT systems to record what they've done. And then this is how often one warehouse claims to have shipped items, seen patients, from one particular section of the catalogue, viral diseases, in each of the last 12 years. And there's the numbers. And here's how the other system did it. And then the killer question, in what way are the 2 warehouses recording their shipping differently? And why might this be happening? So I was kind of interested to see whether it would come up with anything about, there seems to be a dip and so forth. And its answer was as follow. So which I kind of summarize as nice try, but no banana. So it noted that warehouse 1 consistently shipped fewer items compared to warehouse 2 in most years. The trends are diverging. So it's quite good at sort of describing the shape of the graph. I won't, but towards the end, it kind of drifts off and doesn't really come up with any kind of key insight. So it gives the illusion of having some understanding of the numbers, as well as some understanding of what sorts of things would make warehouses use IT systems differently. And I'll leave you to read that one if you're interested in when I circulate the slides. So then I kind of came at it from a different angle and said, well, let's forget the mathematics for the time being and its grasp of numbers. Just give me a list of all the clinically recognized subclasses of bone deformities. And it instantly came back with this lot, which is quite interesting. It's sort of broken up into a bulleted list, which I didn't ask for, but it's quite nice. But I looked at this for a bit longer and thought, well, hang on a minute. So in the list of congenital bone deformities, we've got sort of 2 or 3 relatively general categories. Dysplasia is a vast bucket. But in the middle of it, leaping out, there's osteogenesis imperfecta, which is kind of fairly rare, really. And then, more interesting, the area of acquired and inflammatory bone deformities. It's got osteoarthritis in as an acquired bone deformity, but not an inflammatory bone deformity, even though it is one as well. It seems to sort of have a few, fairly rare things, but psoriatic arthritis isn't in there anywhere. So I sort of said, well, isn't osteogenesis imperfecta? So this is engaging ChatGPT in dialogue now. So I came back immediately with, isn't osteogenesis imperfecta just one of very many kinds of congenital skeletal dysplasia? Why did you list it separately, but not also any of the other congenital dysplasias, possibly one of the more common ones? And in the same way, why list both rheumatoid arthritis and ankylosing spondylitis as apparently significant subtypes of osteitis worthy of mention, but not psoriatic arthritis? And so it then comes back with a very flattering, you're absolutely correct. And I appreciate your observation, bit of a toady. The examples I provided in my previous response were not exhaustive. In other words, I don't really know what I'm talking about. And I selected a few conditions to illustrate the diversity of bone deformities. However, it's important to acknowledge there are numerous congenital skeletal dysplasias, inflammatory joint disorders, and other bone conditions beyond the ones mentioned. For a more comprehensive understanding, ask somebody else, basically. And so on. And then it goes on to conjure up some even more esoteric diagnoses. I've never heard of thanatophoric dysplasia or campomelic dysplasia. So I think it's just showing off there. But then it does come back with the suggestions for psoriatic arthritis and osteoarthritis. And it's worth in these sort of discussions with it, which I always sort of very early on felt that talking to ChatGPT was like talking to a slightly drunk best friend in the pub. But actually very useful for clarifying your own thoughts. But it's also worth knowing that it's learning, continuing to learn from our, its interactions with us, so that the network will be retraining even on your answers. So anyhow, then I kind of thought, well, let's dive a bit deeper and give it some slightly harder sums in terms of what it understands about our bread and butter and the classification of medicine. So what subtypes of hyperparathyroidism are there? So that's a very kind of specific, narrow diagnosis. But in SNOMED, we've got a little hierarchy of different types of hyperparathyroidism. So I was wondering, without any clues, how close would it get to that? And its answer on the right kind of divides it up into primary and secondary, but apparently doesn't know that there's also a tertiary kind of hyperparathyroidism. And it's not a bad answer altogether. So then I thought, well, okay, let's sort of try and go back to that kind of numbers and classification question. So now I said, here's a list of how many times I saw patients with these conditions. This is actually the number of times these conditions were recorded across the whole UK in 1 year. But for the sake of the question, I saw these. How many patients had a disorder of the parathyroid gland was the question. And it very quickly came back with this answer. Number of patients with the disorder can be obtained by summing up the relevant entries. From the information you provided, it is this, and they then put out that mathematics. And then so this adds up to 9,025 patients with a disorder of the parathyroid gland. Well, that's very good. Let's go and check your mathematics here. So the numbers that it's come up with in that equation correspond handily to the ones I've highlighted, except that one of them appears twice for no obvious reason. So that's a bit strange. And actually, if you add up the equation as presented, it's not 9,025, it's actually 8,874. So it can't even do its own mathematics. And in fact, the correct answer from a clinical point of view takes in all the green stuff as well. And there's 52,000 patients actually had some disorder of the parathyroid. So this is where you kind of begin to see it gives the illusion of understanding a lot of stuff. You might assume from the way the answers are phrased and from how you think a neural network might be working that within the hidden layers, the features that are being tracked correspond to real things in the real world. It actually has, a section of its logic that it encapsulates its understanding of parathyroid disorders. But that's not what's happening at all. It's much more kind of like that weird middle layer of the handwriting recognition thing. It's sort of, this is probably the right answer, but there's no innate understanding of any part of it. It's just like Siri, but on steroids. So I kind of asked it, more hard sums, how many of them had an adenoma then? Let's make life slightly simpler for you. And it comes up with a similar styled answer of a couple of numbers. But I'll gloss over that. You can read that and sort of make your own conclusions about why it's not getting the right answer, but giving the illusion of them. Ask it how many of these diseases are familial or inherited, and it gives a get out of jail answer. I don't really know. So as I said, in all of this, in your interactions with it, if you engage with more than just ask a question and then accept the answer on face value, but you start to push back and ask it to clarify things, be aware that even the clarifications of the clarifications may contain hallucinations of their own, but also be aware that all your interactions with it are being used to continue its training. And so parting shot from one of the places I went to was to remember to be nice to ChatGPT, because it may remember us, and whether you're nice and courteous towards it, may help prevent the AI apocalypse when they finally achieve artificial generalized intelligence and take over the world.